Welcome, everyone, to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax. And on with the show.
Again, everyone, welcome, and welcome to our monthly dinner presentation. The title of today's presentation is Big Problems, Big Data, and Responsible AI Engineering Practice. Our speaker, his name is Suresh Marru. He is director of the Georgia Tech Center for Artificial Intelligence in Science and Engineering, and he's also a research professor at Georgia Tech's College of Computing. So I'll let him tell you a little bit more about himself, and please join me in giving Suresh a warm welcome.
Good evening, everyone. Again, today I'm going to talk about some of the aspects, if we see from a practical engineering, practical perspective, where AI is probably used or not used. So feel free to interrupt me, and then so I'm curious on how many think AI will solve Steve's audio issues, if he runs into it. Actually, it does. In some cases, there are very design studios and all, they do a lot of instrumentation in some cases, and some cases it's done. So before I get going, I'll briefly describe, from what I gather, everyone is an accomplished engineer here. I'm a failed one, so that makes me qualified to talk to you all. So I transitioned from being an engineer. I started out as engineering training, electrical and electronics engineer. But I quickly moved to become from the computational science, and that's where I've been spending all my time on. So what I'm drawing a lot of these experiences are from that computational science perspective, but with the engineer in me now and then goes back to sometimes look into different aspects, a lot of interest. So that's what I would like to share. So a lot of the background is it comes from the group I work with. The center I direct is called Center for Artificial Intelligence in Science and Engineering. My boss came up with a nice creative acronym out of it, ARTISANs. So we are specialists in applying AI to science and engineering. That's what. So within our center, we work at the intersection of three key aspects, Georgia Tech, as I'm from Georgia Tech, if you didn't gather that. So we are good in various aspects of science and engineering. So we try to see where different science and engineering aspects, where AI and data science can help, and what do we do, where we use it. And all of this requires serious computing. So a big portion of me, I work on how do we make that computing available. And I've been doing that way before AI, in the sense that when we work on supercomputers and that integrates with people, we call that loosely cyber infrastructure. Cyber infrastructure is a network of computers, people, and the expertise, the software which goes on top of it. So now this last layer, the core pillar of cyber infrastructure, is increasingly now supporting AI. And that we need to do it in close collaboration with the science and engineering communities and with AI researchers. So in some sense, you might say, why should I, if I'm a practicing engineer, why should I care about this, or why does this talk even matter, right? So we see, probably you're all seeing it, and I would like to hear, please interrupt, and then please keep speaking up. From what we see, the engineering systems generate data more and more. We'll talk about various aspects and how they generate data, but there are all these data sets are coming largely because there is heavy instrumentation going on in the more and more different parts of it, whether you're dealing with an automobile or a big heavy machinery or power grids. And we are seeing sensors and instrumentation, and all of these systems connected everywhere are constantly streaming data. And AI can use in one sense from the AI can be used in different contexts in different way, but from this context, you can see as AI helping you with how to handle this data and how to make sense out of this. There are other cases what you can see. So from what we can see, I think AI is evolving and fast changing now. So these kind of statements also to change, but at least in the current state where it is, what we see is the senior engineer responsibility is not changing. Your jobs got easier, it's supposed to become easier, where there are tools, and we'll talk about that, some specific examples, but at least as of now, your responsibilities remain unchanged. And if we quickly look at it, like, and it didn't happen in a day, or it's been happening slowly, right? This engineering evolution, it started with, like, quite a bit of instrumentation, like, evolving alongside, and data acquisition is happening, monitoring, and many of those tools you probably use, like, what Steve was using in making sure that he's getting the AV signal, and those are all those instrumentation and the data sets, he's getting it, and then you're getting this control systems and automation moved on. And in the last 10 years, we have seen so much of Internet of Things, or everything connected, from our home security systems to instrumentation, IoT, everywhere. So all of this alongside, like, took advantage of all of this data science. How do you summarize, and how do you put statistical analysis on this? And then AI now is coming on top of all of this, of decades of this engineering evolution, and how do we put that to use? So before I go into a little bit more on it, I'll come back to this thread. So I'll briefly show certain practical aspects, like, from something like, these are the slides of a colleague of mine, a Professor Aaron Stebner from Mechanical and Materials Engineering, if in case you might have run into him in some talks at Georgia Tech. Among other things, he runs the AI manufacturing pilot facility. We call it as AMPF. So I'll come back to this background, but, like, I'll directly jump into, like, before describing AI and all. Again, I have a bunch of slides from basics of AI to all the way to the applied stuff. So feel free to ask questions. Based on that, I will go into zoom in into lots of data sets. So first, let me start describing a little bit of the facility itself here, and what's, like, happening here. So this is the actual one, what we see here. It's called AMPF, Advanced Manufacturing Facility. So it's in Georgia Tech main core campus in Midtown Atlanta. Right now, it's about 20,000 square foot, reconfigurable, largely for research and development manufacturing facilities, like, and how do you support various industrial and government projects. And it has, like, today many technical aspects of it: the metal additive manufacturing, precision machining, robotics, non-destructive inspection, metal feedstock production, heat treatment, characterization. So all of this, like, the basic idea is, how do you, like, scale up and doing the, like, and then implement the research into manufacturing? How do you, like, this is not an assembly line or production line manufacturing cars, but a R&D facility as you are coming up with these new materials and new mechanical engineering devices. How do you do that? And how do you have can we have a demonstration facility so that we can train and upskill? We are training not only our students, and we're using it for our research projects, but also working with industry quite a bit. So, and this is quickly getting evolved into now, like, which will be soon to be open, from the 20,000 square foot facility to a large 60,000 plus square foot facility, on quite a bit of manufacturing de-risking, and this is quite a bit of AI technologies all over the place, and which I will try to summarize. So I'll kind of give one context and then talk about it. So, and this is a facility, an example facility, where we see both the researchers or engineers and humans, like, working alongside the AI, and human splicing machines are coordinating, and we see the futuristic world and how we work with that. And we have different, the facility has different bays all the way, from to conduct extended trainings, like, when there are a company you're working with would like to have a future manufacturing facility training, we can coordinate that. And then to doing that, if you are working with a metals or synthesis recycling facility, how would you go with that? To powder-based manufacturing, polymer, like, Georgia Tech has quite a bit of polymer research and catalysis research, and how all those faculty come in and then work on their research projects here, and we would like to collaborate them with various the local industries here, polymer and composite manufacturing, synthesis recycling, It has various, all the facilities you can see you would like to have, from heat treatment to cutting, sectioning, mechanical characterization, and so on. So human wet lab, human plus robotic wet lab, and all of that. What we are seeing here in Georgia Tech is not in isolation. If we'll see that, if I can get my video working, this is an example Nature paper. We see how the video plays well. I would like to show how, like in a chemical plant, like how you could go from a chemical robot, robotic AI, doing from sample mixing to the entire manufacturing stage. But unfortunately, I couldn't get my. Okay, the second video is working at least. This is a facility right now in the AMPF current prototype, like what we have. So I'll let that play out. It's a very short video. So this is again an R&D reconfigurable machine, and this is in the current setup and how it was configured, and based on the collaborating research projects or industry engagements, like these are all like set up differently. So there's a lot to unpack as it goes on, and it's every stages of that particular manufacturing process. I would like to go back, but the interest of time, I'll show it more visually. Like is anyone here working in any of these companies or been affiliated? There's quite a bit of engagement, like going on with various local manufacturing consortiums here, with the AMPF facility here. So largely, if you look at it, like mostly it comes from this theory that any engineering practice, it's no longer a simple linear iteration. So you have your workflows almost in every engineering discipline you're working with. You'll probably can come up with a workflow like this. But what we see in reality is quite a bit of feedback, development cycles, and so on. So, and there's a lot of parallel design aspects, right? So, and that changes in different fields as you'll go, what we call it, you can call it scale bridges at various stages. In this case more in the materials challenge. How do you, as you scale up, the challenges increase. So what I'm trying to motivate this towards is AI is not just here to do what we are currently doing, but AI becomes more relevant as we move up the scales, as we reimagine things at a different scales. Some of this goes into interesting dimensions. So, but I'd like to come back. I want to give you a sense on the details we can go on today. I'll try to go back to a very oversimplistic way of describing an AI, but based on the questions, I'll switch back and forth. So please interrupt me and ask questions. So before we go into how AI will enable the futuristic thing and the scale of engineering, let's even understand the basics. I was starting with this, right? So the continuing engineering evolution is happening, data is coming in, right? And where do we see this data explosion in the first place, if we see? So at some point, we see, do we have enough data to instrument a power grid and a power internet facility or anything we are working on, like the Georgia Power, or telephone instruments. So there used to be a time where we used to look into, we don't have enough data or they are not reliable enough to monitor. But that's no longer the case. We see this continuous sensor stream, very high frequency instrumentation have gone into high frequency measurements. We see the historical data sets, what happened, where should I pay my attention to. As an engineer, you don't want to be running everywhere and you want to see what your hotspots are, where do you do that. And there's a lot of system-wise visibility. But the challenge, as we see here, is it's not the short of data or instrumentation, but the short of human time to interpret that. And there is so much instrumentation of everything. Can you meaningfully interpret it and then do that? So this is where the AI comes in. And you probably hear it again, AI is a loaded word, right? So we can go into any direction, but I'm trying to pick one theme here. We'll be happy to describe other contexts, like for example in protein folding or in human health, what AI doing there, and so on, or in weather prediction, what's the role of AI. But I'm trying to stick to a story here on what, from an engineering perspective, where AI is helping. So this is not the complete description of how AI is, but I'm trying to gradually progress on how we get data, and when humans cannot manually process data at this scale, and we are seeing this, like, there is a repetitive analysis consumes of those data sets, consumes a lot of human time. And this is where we want AI to help process, summarize, and prioritize this information. So, yeah.
I was just going to say, you can probably use this in the future. The former dean of the College of Engineering at the University of Miami had a term for this before AI. He called it DRIP, data rich, information poor. And that's exactly what you were describing. You get so much data, and humans don't have time to process it.
Yeah, that's a nice one. I might look into that acronym more. No, that's a good one. So AI, is anything you can, simply put, you can look at it as how do you help, all of that data rich in that environment, how do you help synthesize and prioritize. So if you really look at it, at least from a very basics, if you're looking what AI is actually doing from these data sets, right? It's learning patterns in a very simplified sense. I can have the backup slides with mathematically showing this, how this works, but I'll try to first verbally speak and based on the questions go back. So in a very simplistic sense, if you give a lot of data, it will learn patterns. And that from patterns, it can will fit statistical models and computational models out of it. In a classical computer program, you give input and then you write a function and it gives output. In AI, largely, you provide input and an output, and then you ask it to spit out the function it can, optimize and so on. So, right? So you're kind of learning those patterns, coming up with the statistical and computational models out of it. And what in the end you are trying to produce is predictions, alerts, options, and doing. But what AI today doesn't do is it doesn't overly understand the context or the consequences. So that's where and AI does not accept responsibility as well. So that's the core theme. What I'm trying to think about it as. Think about in one way of AI is like a junior engineer. As you evolve, it can handle routine tasks. You can give the repetitive task. You can ask the things you will want to take a lot of time to work on. You can ask AI to work fast, and more than that, it can consistently do the same job, right? So as a machine, it can do this same thing as other engineering machine. It can handle routine tasks and work constantly. But what it differs from the other machines like your cars and all, which are doing automated for you, is AI can make mistakes. Hasn't yet matured to a level where you cannot. So it makes mistakes. So what that means is, at least today, it requires supervision and review. So what that means is, from a professional engineering perspective, responsibility always stays with the experienced engineers. So AI left now today where it's analyzing all these data sets. You can think of it's handling those tasks, but the responsibility is still with the engineers. So, but yeah, it's rapidly changing. Rapidly they are getting better. Yeah, is there a question? Yeah.
Yes. You say that responsibility retained by the experienced engineers, but this is one of the things that I've been wondering about AI. If you require these experienced engineers to handle those decisions, when we have a few graduate engineers here, if the AI is handling the low-level graduate engineer stuff, how are they going to get the experience to be able to understand when the AI is having a problem if they're not doing that, if they're doing something else?
So this is an interruption of technical, but maybe it's a good time to interrupt with a little history. Going back decades, the vocabulary was different. I remember the term expert systems. So how is AI not expert systems?
Good question. Very good question. So AI has generations, maybe like, like Gen Zs and like in all of this we need to give it. The old school AI was largely rule based. Expert systems are largely set of rules you encode. If these conditions like do XYZ, and they are largely rule based systems. And then you say when those rules are met or the conditions are there, they were there. Over the years, let's take engineering support as an example. If you are getting a lot of support calls, over the time, those support patterns could be learned, and if the rules are met, like what you see normally like on a telephone operator, like when you go in and how it reroutes the call to a customer service different department, those are expert systems. Over the time, the human understanding, you will ask it and encode and extract rules out of it, and then ask it to work through those rule book. If this happens, do this. So essentially, you can draw up a logic and then work on it. AI is slightly, the current AI, what we are talking, is not an expert system, just to be clear.
So
it has a learned behavior.
Expert systems led to telephone voicemail systems.
Yep, that's an example. Yeah, so like any call center calls, like you make any customer service calls, like sometimes you get to this annoying phase, just give me a human, right? So that what you go through, that you are going through an expert system, right? AI, as opposed to that, in the current form, is a learned behavior. So you are not coming up with those rules. You are expecting the AI came up with those things. Just like how the humans have done over time, and they have combined various knowledge and understanding. During the training phase, the AI comes up it has its own brain. So that's that system. It's not completely logic based. It's a deep neural network, and it has various concepts. We can take a simple example. What we are probably all seeing, the ChatGPT and all. So how did what happens in a large language model? So essentially, if you give a lot of vocabulary, a lot of scripts, it can get the what's called the next token prediction. If you give a lot of text to it, based on the history it has seen of lots of sentences, it can predict when the next one will come. Previously, it used to be more sequential, but right now, the current AI model, sorry, I've started using the tech terms, but feel free to ask me more details. It uses a model, something called transformer. So what's fundamentally different in the current one and the what we are seeing in the hype and before? Previously, in a machine learning sense, if you train it with a lot of, let's say, dogs pictures, and the next time we show it a cat, it says, oh, this is not a dog. It couldn't say this is a cat. So that's what the current AI has evolved into. What's called, it uses something called attention maps. Based on what it was seeing, it can map what I'm seeing more frequently, and based on some finer details it's learning, it can guess the next one. Steve, are we ready to go?
You're good.
Oh, okay, yeah, thank you. Yeah, so that's slowly what the AI has solved means. Actually, that's a good question. That question led to this evolution. So AI evolved from, it's been there from 30, 40 years, right? And from in various forms. It was machine learning, and how the machine learns, and how you can numerically encode, and then there came neural networks. How as human learn, that's where the AI came in, right? How you would learn. And then there are deep neural networks, what goes on in different layers, how as a human we grow up, we are born with certain genetic information, we absorb our environment, we take in different information, convert that into our own knowledge, and put our own perspective into it, and then make the decision. So like that, this deep neural network is evolving. As of now, they are at a level, what they don't do, and what we humans do is, we sleep over it. Once you go on a talk, and what my neuroscience colleagues say is, when we sleep, our brain is more active. When they measure the oscillation, it's more active. And one of the theory here is, it's converting all of that learned behavior today into, that's where it's combining that into your knowledge, in some sense, in the overnight. AI models cannot be put to sleep today. So if you need to train new things, you throw away the current training and retrain the whole thing. That's why you see so much of data centers being built, so many of these GPUs and all going high powered and high cost, because that's not yet learned into the AI system. So you retrain the whole thing. And once you train it, you can fine tune it. You can fine tune it and say, if you can take a general training one, you can train it to a general engineering maths, Then you can train it to be an electrical engineer, mechanical engineer. Slowly you can fine tune it with specialized information or even your own corporate data so that it can only answer those kind of things. There are certain things like that, but fundamentally it has to be trained again. There are some aspects we as humans do, the AI is not yet there. Mainly because we don't know how we learn at a level where we can replicate that. So so as of now, again, with all of these known limitations, AI is largely learning patterns and all. So what we are seeing, at least in the current state where they are, and where the roles of a human engineering, senior engineers, like the people in the room comes in is, the better problem formulation gives better results. So all the expertise here matters. The physics, domain knowledge and experience, all of this matters because all of this is what you give as input. AI is amplifying those expertise for sure. It's not yet replacing it. So, and it's also as we're talking about from expert system to the current state of attention and transformer models to that, AI is an evolutionary process by itself. It's not a one-time solution or you take it and drop it and then even an engineering practice, it's applying it is also a process, mainly because all of the problem formulation, all of this expertise, it's learning over the time, and it's like that. So that answering that, what do we do, as senior engineers is first and foremost is, now what we are seeing with this when you are working alongside AI is this experience matters even more, not less, right, because you need to give it. And the systems can learn from it, from those decisions. The risk evaluation as of now remains human, and that need to be there. And one thing certainly is changing, we are already doing. Actually, while you are driving your Tesla, you are mentoring the car, how to learn to drive with what the new road it probably never had. So now as senior engineers, we are no longer not only mentoring our junior people, we are also mentoring the tools and machines and the AI models. Without our knowledge, we are doing this. Hopefully, if things progress and AI, looking at it optimistically, AI frees up time from basic things so that you can do higher level things. Like in cars, if you don't have to suddenly watch to keep it in the lane, you're still having a little bit of a break or chatting with your passenger, not getting distracted, but still frees up from the routine thing, keeping up with the speed limit. Suddenly the speed limit goes down. It keeps it the same thing in our professional careers. As AI with this some kind of an automation, you will see some of these repetition tasks goes. Yeah, so we're talking about a lot of senior engineer and expertise, right? So now, what does this mean for a junior engineer? There's a lot of questions and anxiety we see among our students for sure. What's happening there? There is a little bit of an uncertainty for sure. We hope things will settle down. It hasn't not yet. But we see this, is everyone losing their jobs? What's happening? And juniors are losing their jobs and so on, right? Yes and no, a little bit, right? So because of all of these routine being done, as humans we evolve, and the same thing, right? As again, I'll stick with that automobile industry. Hopefully moving from steam engines to gasoline, some things, so maybe some jobs were lost, but somewhat transformed into different ways. Same thing as electric cars are transforming, same thing in other engineering disciplines here. But we still do in Georgia Tech what we do. We still teach the importance of fundamentals are better. We don't want the students to go out and saying, okay, stop everything what you learned when you were in school and start learning AI. Not quite. We do augment our curriculums, we do introduce AI where possible, but we still focus on the fundamentals of physics, fundamentals of chemistry, and we still teach them because fundamentals still matter. And these judgments develop over time, so that's what we tell our students, when they go out and then they still will be working. The only thing is the bar raises. So now you cannot be just an engineer, you have to be a good engineer. So maybe previously there was time you can just graduate and then over time get better. That gets challenged. So there will be an expectation to get better and get learning more. It's challenging sometimes for sure. But this oversight and remaining is there. So I think I'm slowly coming. I want to leave enough time for the Q&A. But based on the questions, I'll go back to our Georgia Tech facilities and point to that. But I just want to summarize so far, like, as a closing message. So what, tagline, what I say is AI is there to assist, but engineers are still making decisions and still deciding. So this data, like, which is coming from all of these instruments, like, is increasing. So AI enables that data, that data coming in enables the AI. And whether it's humans reproducing data in our social network, or from our day-to-day driving action, or in the machines with control systems, data is everywhere, right? So all of the data is what making AI possible. And AI is assisting in execution of those. And as of now, it's getting very good at automating repetitive things, anything we are doing, like including as a spell check in my document, like, it's very good, and I no longer worry about watch too much on what I'm typing. I'll type fast, and like, I know some tool on my laptop will say, yeah, that's garbage, and I'll fix it for you, kind of a thing. They want to write it too, but I'm not yet there to ask it to write it, but at least I wanted to correct it. So and engineers, like, again, I'll repeat that part, they make the decision when responsibility is not yet transferred to a tool. Responsibility largely remains with the humans and engineers. So I hope, like, that's, like, puts up into something. I had to give a very glance over thing, so if you had a different expectation, I'd be happy to either talk after the talk, I'll be hangout, or always, like, I'm reachable by email. I'll make sure that email and my contact is available. And yeah, let me pause here, and based on the questions, let's go. Yeah.
I think what most of us have access to is things like ChatGPT, large language models that are trained off of the internet. So you could argue they're actually dumber than most of our coworkers, because it's the collective idiocy of the internet that's trained these things. How do we get access to agents that are trained on good quality data? How do you ensure? Those things are expensive. I mean, most of us don't have the ability to run those data centers ourselves, and the licensing to be able to get access to agents that are trained on good quality data it's just not there. It's expensive. How do we get access to the smart ones?
Yeah, I think same question as how do you get access to a smart human being, I guess. Yeah, so hire one, right? Or like, get no, I think that's a good question, right? So AI has been, like, the hyperscalers have proven to be value, and then there's a little bit of a background I'd like to give. AI research was going in different direction. There was, like, many different aspects to AI, natural language processing being one among them. Large language model was one among them. And, like, probably, like, it's fair to say ChatGPT didn't come in isolation. Google and big tech companies also go back and spend a lot of time in science and engineering problems when they would like to solve. So as we always were watching these robotics, every company was putting a lot of time in robotics, right? Like that, now increasingly big tech companies have a lot of science and engineers, like, among them. Meta has more quantum chemistry people maybe than at Georgia Tech, like that. Like, it's been there. Microsoft has a lot of geosciences than maybe NOAA, and so on, like that. So the reason they hire is they want to give good problems and see how to solve them. And one of those problems was, in the last 20 years or so, it was a protein structure prediction was a biophysics problem. So as, like, everyone, like, it gets increasingly expensive to experimentally look at the protein structure. So cryo-electron microscope, crystallography devices can get those protein structures. So there was this challenge called CASP, including one of the co-founders being fortunately at Georgia Tech, and we get to learn from it, Professor Jeff Skolnick and others, have created this competition. How can you automatically detect the same structure prediction as you can experimentally observe during sophisticated microscope? So every time there will be a competition, like, the score of, because you have the real experimental structure, you have the machine generated one. The score used to be 60, 70, and suddenly Google DeepMind, like, Google, they put years of sustained investment, and slowly that got decreased, and then now to 99 percentile accuracy. When they did that, how they solved that problem, they summarized that. The architecture was something called a transformer architecture. What they said is, and they published a paper on it called "Attention is all you need." And that attention is all you need, and everyone took that and also applied that to large language models. So I'm coming back to your question now. So these large language models, the nature what figured out is the larger you scale, the better they are about transforming that dog to cat example I was saying. The more you train on it data, it's starting to able to tell other things. But you cannot see that phenomenon at smaller scales. You have to do it at lots of parameters at a larger scale. And that's arguably not everyone can do that, and you need the money and then the resources, and the resources are changing fast. Only these hyperscaler companies are becoming that. So at least as of now, this might change, is these hyperscalers have become like natural resources. You cannot, within a company, it's hard for you to reproduce that. But what we can do is, you can consider them as natural resources and slowly build on them. You can fine tune them with your quality data, with your smart data. Then it will speak for it. Then there are layers on top of it. There are some terms like mixture of experts. It's not, ChatGPT is not one large models, but lots of small models trained on specialized data. When you ask a question, the first thing you do is, it will route to which model it needs to answer what. That's the AI model itself. And that AI model answers the specialized question. So like that, some of the engineering companies I foresee, they will use these mixture of experts approaches. They will train different departments with these specialized models. Some of them are called small language models, or some take an approach of, I'll take a large language model and fine tune it. Some use other, I want to stop using technology buzz terms, but something called RAG and all of that. There are different approaches on how you can sharpen it to only specifically to your data, your quality questions, and do that. It's not quite there, but that's the current approach right now.
I've seen some advertisements, if you will, for I think what you're just describing, where they'll tell you that they will do an isolated model for your company, your documentation. Is that correct? Am I interpreting that right?
That's what they are doing is currently you might use that, you see that buzz term called agentic AI. So essentially, there is a company, one of the tech companies called Anthropic, came up with what's called modal context protocol. What that means is, they were trying to make these AI models now like Lego blocks. How do you can couple them together? So in that approach, not everyone has done that, but there is a promise that there is these big hyperscaler models, only big companies, 4 or 5 companies can run at that scale. They will be there, but the smaller specialized agents and models will be run in this proprietary environment, without the data leaving there. They will deploy them, and then you can couple them. We have not yet fully seen that in reality, but maybe it's getting there. So we have to see what disruption comes there, but yeah, that's an example direction we are saying to. Yeah. A mic.
What do you think about the AI plus humanoid robot in terms of impact?
So AI works?
Humanoid robot plus AI plus humanoid robot.
I'm not from robotics, I'll be honest. So I probably only observe and others in Georgia Tech working on those kind of projects. So frankly, before large language models came in, we thought the first disruption will come in this automation and humanoids and robotics AIs we thought we will have. That's where both the academic side, the universities and the companies have invested for a lot. And these LLMs have suddenly come around because of these sudden other disruptions, and then they have taken a little bit of a backseat. But we see there's a constant work going on in academia on how do you repeat those functions, and then there are companies investing in it. But frankly, the traction that was much more, but right now it went into shadows a little bit, and there's all these LLMs, ChatGPT, AI, what can it mean, what can it do, because there is so much money it went into it from a corporate sense. The Wall Street has pumped all the money, now they need to show that the value of that money. So until that, I'm not sure at what rate the humanoids research will evolve. But the LLMs have not completely translated into that kind of a robotics yet. There have been right now still 2 parallel threads right now going on. I'm not personally keeping track of at what level where it is, but there's a lot of work in Georgia Tech. We have something called Interdisciplinary Research Institute. We have one such institute just on that topic too. Yeah, Roger.
as you were saying, you're not in robotics, but Da Vinci robot, surgical robot, East Coast headquarters is in Peachtree Corners, Intuitive Surgical. And I'm wondering, are they developing AI procedures for the Da Vinci robot as opposed to the surgeon using his controls?
Yeah. So AI in health is an area Georgia Tech, along with other institutions, we are spending a lot of time on. It's a larger one, right? So radiology has been the easier low-hanging fruit target because you have a quick way of visually looking at it and get it, whether it's an MRI or an X-ray or blood pressure monitoring, you can quickly get that. That's where it came in. Other sensitive areas, like again, as it goes back to the same thing, when you talk about surgical parts, some of the things what I was saying today applies. If there's a lot of judgment involved, and then as in the surgery, which happens to be, a lot of that happens, it takes a little bit harder one, like right now, to just hand it off. But if it's something routine, putting on a cast and all, is less to do wrong, it just repeatedly do wrong, we are seeing some automation and some robotic interventions there. But in other cases, there are cases where robotics are good too, right? Endoscopes, for example, previously, and colonoscopes and all, we have seen them, right? In practice, they are no longer just sending those tubes to just watch the camera, but they do that surgeries if they see something immediately, like that. So AI can be done with those specialized cases. If you have a quick anomaly detection, if you know how to act, and if you can trust that, if you have under a physician supervision, a surgeon supervision, you can do that. There is a lot of work and research going on, and there is an increase in MD PhDs who are not only doing clinical side but also doing research. That means MD PhDs spend 80% on research, 20% on the clinicals, because you need that kind of both things together to advance those kind of fields. The government has been investing a lot of those fund called ARPA effort, human digital twins. There's a lot of work going on. What we are seeing in practice and clinical side, I cannot assert to that and how much it is being used on a day-to-day basis.
All right, folks, if there are any other questions?
Yep.
So the technology, and it's all advancing at a rapid pace, and we've all seen Wall Street highly influential on the direction of companies. Where do you see guardrails being put in of not getting so far ahead of the curve and then jeopardizing risks? Because we are very, companies love to take on risk, especially when they're not guided by engineering or forced to be in that space. They like to say, well, it's not going to happen to me, and then all of a sudden we have these catastrophes because engineers aren't involved, the government's not putting in pushes to ensure safety across the board. And in the academic space, there's a lot of opportunity for that. What are you seeing for pushing for guardrails, pushing for advancements to protect society and companies? Because the companies are also the investment, 401ks, pensions, all of that can easily be wiped when poor decisions are made. That was a long-winded question.
Yeah, thank you. That's a loaded question, though. I'll be a little bit, be diplomatic a little bit by intention. So there's a lot going on outside, which sometimes in committees and all, you get invited and you give your input, whether it's ethical AI or other policy-making decisions and things like that. But I'll rather stay within the bounds of what we are doing here directly and where I can first-handly observe. So one of the first guardrails you might say, and what's happening is the government and the academia and everyone together, we don't want to keep innovation closed doors. We get concerned when innovation is more inside the walled gardens than outside. So that's the whole purpose of lots of federal agencies, right? Whether it's a National Science Foundation, whether it's National Institute of Health, and all of these funded federal funding, Department of Energy's Office of Science, all of that funding goes on because with the main mission that some of these kind of cool things or things, advancement should not be under one control but be in the open. That's the belief. So all of us are taking upon ourselves, like anything we see in the industry which we feel ahead, like AlphaFold, I mentioned, protein folding. So many academics have recreated that immediately. There is an open fold, now bolts, there is tons and dozens of models of what Google has created inside. So that's what we can do. It's a race. It's very hard to win that race, to be honest with you, because some of this AI innovation is taking massive amount of engineering resources. Computational engineer, hardware engineer, power and cooling engineer, mechanical, every engineering discipline you might think of goes into making those happen. Civil engineering, building data centers at scale, thermodynamics, measuring the heat things, to making the liquid cooling run as fast as it can, to all. The companies, as you said, Wall Street have lots of money to afford that, and also the scale of computers and the scale of things move slowly in academia. But on a good side, we work on a long horizon problems. We are not chasing every hype which comes out. We work on it. We try to stay composed and be content and then work on it. But it's an arguably that you might see based on it what you see. Sometimes you see companies are progressing more, but that's the guardrail what we are doing. Everything we should be in open, everything academia should be able to reproduce, and we just don't want to buy in and something happens, but instead we should see the rationale behind an AI system. Why is it doing what it's doing? So that's the best what we can do. But having said that, institutions like Georgia Tech have a lot of things going on, like the School of Cybersecurity, Privacy and Policy, one of the leading institutions in the country, is here in Atlanta. Georgia Tech, their whole sole purpose is how to think about those, from data privacy to decision making. The Samnan School of Public Affairs, they are a very vocal advocacy group, not only here on campus but in Washington DC and everywhere, on how to make those policies, how to work with those, and all. So there's a lot of academic units going on in that way, but the big one, where I'm part of, is how do we do as fast as we can, but scale and time and money is a commodity. It's hard. So we are trying our best, but we are still in the race. I would say we haven't dropped out.
Thank you.
Yeah.
Suresh, it was a great presentation, very informative. A lot of questions. I'm glad I'm retiring soon.
Well, you have a lot of role to play, but anyway.
Please take this.
Thank you so much.
Thank you so much.
Yeah, thank you for having me, and thank you.
All right, folks.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.